Well, hello and welcome to our journey into linear algebra. And in this section we're going to be looking at some of the applications, or one particular application of symmetric matrices. We're going to start out by looking at a simple problem of sketching this curve 5x squared plus 4xy plus 8y squared equals 36. Well, it's not quite clear how to even begin a problem like this. It's some kind of what we're going to call a quadric surface or quadratic surface. But it's not clear how one can draw this except perhaps to use technology, and that's exactly what I did. So I got the computer to sketch this, and this is what it produced. And you can see from this, if you slightly turn it on its side, you can see that this is looking very much like an ellipse, except the axes are no longer, the x and y axes are no longer the major axes. So that raises the obvious question, is there any simple way of being able to tell that this is an ellipse, and if so, to sketch it, and how to find what the so-called principal axes of this conic are. And at first glance you might think there's any great connection with linear algebra, but we're going to get linear algebra into the problem by simply rewriting the equation in this form. We're going to rewrite this quadratic form as xy multiplied by this matrix 5, 2, 2, 8, xy. Now you can see where the matrix is coming from. When you were to multiply this out, this x multiplies this number here and this x to give me the x squared term, and that was 5. And similarly, this y multiplies this 8 multiplies this y to give me the y squared term, and that's 8. And there's a 4 there. Now this x will hit this number and the y, or this y will hit this number and the x. So I could have put 4 here and 0 here. I could have put 100 there and minus 96 there, as long as the sum of the two adds up to 4. But it's convenient to share the 4 equally between these two entries. So I halve the 4 and put 2 there and 2 there to give me a total of 4xy. And the point of doing that is that this gives me now a symmetric matrix. And you'll recall that a matrix is symmetric if it equals its own transpose. So if you take the transpose of this, that is, you flip everything around the main diagonal, it doesn't do any damage. So we can also write this now. I'm going to write vector x for xy. I'll call this matrix A, and there's vector x there. So this is so it's vector x for this vector xy. So this is the transpose of that one. So vector x is xy and A is this matrix. And I've chosen the A when I wrote it in this form so that A is a symmetric matrix. So just as a simple example of that, we're going to just take this equation and write it in matrix form, and that's a fairly easy exercise to do now, so I'll just quickly go through the calculation there. You might like to try it yourself before looking at the solution. So all I'm going to do is I'm going to write this as xy. We've got 4x squared, we've got 9y squared, and I've got a minus 6 in the middle, and I'm going to share that equally in two lots of minus 3's in here, and that equals 7. So we can take these conics and we can write them in matrix form. Now we just noticed that if A were a diagonal matrix, then the curve is very easy to classify. So for example, if I had the matrix A was minus 6, 0, 0, 2, then when you expand this back out again, it'll correspond to this conic here, minus 6x squared plus 2y squared is 36. And you can see that this one is going to be a hyperbola. It's got one negative and one positive sign in front of the x's and y's. So that would be nice if the matrix A were diagonal. And so what we'd like to try and do is to take our general matrix A and diagonalize it. Take our given symmetric matrix A and diagonalize it, and then that may help us to decide what sort of conic it is. So I'm going to do a fairly extended example of that, and I'm going to come back to that initial conic that we had, and I'm going to work through as what one might do with this. So there was the original conic that we had. There it is in our matrix form. And the first thing I'm going to do is I'm going to diagonalize this matrix A. So how do we do that? Well, we do it via the eigenvectors and eigenvalues. So we set the determinant of A minus lambda I is 0. This will smoke out the eigenvalues of this matrix. So you subtract lambda off the main diagonal, take the determinant. Notice that when we multiply this by this, just to make the algebra easier, I take a minus out of here and write this as minus lambda minus 5. And I use that minus to flip this around as to lambda minus 8, and then we get minus 4. We expand it out, get a quadratic, simplify in the usual way, solve the quadratic, we get 4 and 9 are the two eigenvalues. Now we get the eigenspaces next, so I take the eigenspace of 4, so we put 4 back up into this matrix here and get the kernel of that matrix. And you can see immediately this will be 2 minus 1 is the basis for the eigenspace. And for 9, we want the kernel of this matrix, and we see that that's the span of 1, 2. By the way, note that these two vectors are perpendicular, which is, we're going to see, happens all the time. That's a lovely fact, that the eigenvectors from the different eigenvalues from a symmetric matrix turn out to be perpendicular. I'm going to go one step further. I'm going to normalize these. So I'm going to divide each of these by their lengths, and the length is 1 on root 5. And I plonk these into a P matrix. So this P matrix then will diagonalize the matrix A. So I've normalized the eigenvectors. We note that they're perpendicular. And we also note then that P is an orthogonal matrix then, because these are perpendicular and they each have length 1. So by what we saw in the previous section, this P is in fact a rotation matrix, well, provided its determinant is 1, and 4 plus 1 is 5 on 5 is 1. So this has determinant 1. So P is in fact a rotation matrix. And indeed P inverse is just P transpose. P inverse is just P transpose. So not only will P diagonalize A, but it will do what we're going to call orthogonally diagonalize the matrix A. So P is in fact an orthogonal matrix that does it. Now to see how it works, what we're going to do is we're going to make a change of variable here. I'm going to put little xy equal to this rotation matrix P times capital XY. You can think of it like this. These are the old axes, and these are going to be the new axes with respect to which we can draw the conic. Now xy this way is just the transpose of this, so it's the transpose of this, and you know that means you take the transpose of these but backwards. So when we plug it back up into our form that we had before, that we had started off with back here, we make that change of variable, we get this. And now P transpose is P inverse, and P inverse AP will diagonalize and produce a diagonal matrix, of course, with the eigenvalues on the main diagonal. And now we can expand back out again, and we see that 4x squared plus 9y squared is 36, which we immediately recognize as an ellipse. So that was the ellipse, in fact, that we started with. Now, furthermore, these new axes, these x and y, are spanned by the eigen. So there's the picture. This new one is spanned by the eigenvectors. So the eigenvector, the first one was 2 minus 1. So I'll cross 2 minus 1. So there becomes my new capital X axis. and the second eigenvector was 1, 2, so 1, 2 up here. There's the other axis. And you see what this P matrix has done. It's rotated the old axes around to form these new axes, and that's the P matrix. So that essentially is what we're going to do to analyse these conics to see what shape they are. So we just note here that the unit vectors in the xy directions are xy is 1, 0, and 0, 1. And remembering that we put xy as p times this capital X, which was the xy, that simply gives me xy is this vector and xy is this vector. So these are the two eigenvectors, they're perpendicular, and these are going to give me the new x-axis. So this is going to give me the new x-axis, and this is going to give me the new y-axis. So these vectors are called the principal axes of the ellipse. They're perpendicular, they've got unit length, and we can then draw the ellipse in the xy plane by locating the x and y axes in this plane, superimposing them on the ellipse that we've already drawn with respect to these axes. So just to summarise what the key steps were in this up to this point, once we were given a conic or a quadratic curve in R squared of this shape, we firstly write the equation in matrix form, x transpose AX is D, but we make sure we arrange it so this A is a symmetric matrix. We diagonalise A. Now note that not all matrices, of course, are diagonalisable, and we're going to worry a bit about that in a later chapter, but not all matrices. However, if A is a real n by n symmetric matrix, then happily A is always diagonalisable. This can be shown, in fact, by induction on n. So we write this A then in the form PDP transpose, substitute it into the equation of the curve, and we need to check not only that A is diagonalisable but orthogonally diagonalisable, and that means we're going to require the eigenvectors to be to form an orthonormal set. And when we've done that, we can then show that A is PDP inverse with P orthogonal. So when we substitute this into here, we make this change a variable. This is doing it the other way. I did it as x equals P transpose capital X before. This gives us an algebraic form that we can recognise, provided the eigenvalues are real. Finally, we'd like the xy to be a right-hand Cartesian system of coordinates, so a right-handed Cartesian coordinates, so therefore we want P to be a rotation matrix, so we want the determinant of P to be 1. This is easy to arrange, as we'll see when we do some examples on it. Now fortunately, all of the properties that we need follow from the fact that A is a symmetric matrix. And in the next recording I'll go through and list the properties of real n by n symmetric matrix, and we'll see they're exactly the things that we want to be true. That is, that if A is real and symmetric, it's always orthogonally diagonalisable, and the eigenvalues are always real. And we'll do that in the next recording.